All right, welcome. Today, we are going on a pretty incredible journey. We're going to explore the architecture of matter itself, starting with the tiniest invisible building blocks and scaling all the way up to the massive industries that shape our entire world.
So it really all boils down to this question, right? It sounds almost like magic. How does something you can't even see end up building everything you can touch, wear, and use every single day? Well, the answer isn't magic. It's chemistry. And it's fascinating. So, first things first, we have to understand what holds all this stuff together. You can think of it as a kind of atomic superglue. Seriously, without it, the universe as we know it would just, poof, fall apart. And at the very heart of this glue is something called the covalent bond. The best way to picture it is like a firm handshake between two atoms. They agree to share some of their electrons, and this little cloud of shared negative charge pulls their positive centers, their nuclei, together. It locks them in place, creating a stable partnership. That's it. That's the glue. Okay, so how strong can this atomic handshake really be? Well, let's look at a diamond. It's made of just one thing, carbon atoms. But the way they're connected is what makes it so special. Every single carbon atom is covalently bonded to 4 of its neighbors, creating this huge, perfect, three-dimensional network. You could almost say a whole diamond is really just one giant molecule.
And that structure gives it some incredible properties. Check out this number, 3,550 degrees Celsius. That is the melting point of a diamond. To even start to break that network apart, you have to pump in a colossal amount of energy. That number right there, that's a direct measurement of the combined strength of all those tiny little covalent bonds. Incredible.
So nature is a master at using these bonds to build amazing things like diamonds. But what if we want to build something new, something nature hasn't made? Well, that's when chemists get to be molecular architects, using chemical reactions to design and build brand new materials for all kinds of purposes. Think of it just like following a recipe. Let's say we want to make polyester. You start with 2 different kinds of small building block molecules. We call them monomers. You mix them, and they react in a process called a condensation reaction. The key part here is that when they join together, a little molecule, in this case water, gets kicked out. And you just repeat that over and over and over, linking these blocks end to end until you've built a super long chain. And that chain is a polymer. And here's the payoff. The specific structure of that long molecule we just built gives it really useful properties. It's crease-resistant, which is why it's amazing for wash and wear clothes. It doesn't absorb much water, making it perfect for things like sails or tents. And it's incredibly strong and durable, which is exactly what you want for seatbelts and tire cords. See? We literally designed the molecule to do these jobs. But this brings up a really important question. After you've run your reaction in the lab, after you've mixed everything together, how do you know you actually made what you wanted to make? How can you be sure? And this is a huge deal. It's not like you can just peer into the beaker and see the molecules. You're dealing with trillions upon trillions of them all mixed together. You need a way to check their identity, to get a unique signature that says, yep, this is the one. And the tool for that job is a technique called spectroscopy. Here's the basic idea. We shine a type of light on our sample. Now, the different bonds inside our molecules, those handshakes, will absorb very specific frequencies of that light. It's kind of like how a tuning fork will only vibrate at its own special pitch. By seeing which frequencies get absorbed, we get a chart that is basically a unique molecular fingerprint. It's absolutely essential. And this technique gives us incredibly specific clues. For instance, if our fingerprint shows a sharp dip right around 1710 on this scale, we know for sure there's a carbon-oxygen double bond of a ketone in there. If that dip is a little higher, say at 1745, that tells us it's an ester instead. And if you see a big wide signal way up around 3300, that's the classic signature of an alcohol. Every part of the molecule sings its own little note, and together they tell us the whole story. Okay, so once a chemist has perfected the recipe in the lab and has a way to verify the product, the next step is, well, it's a massive one. It's time to scale up, to go from the lab bench to a giant industrial factory. And it's really amazing to think about. Every single major industrial process, the ones that pump out thousands of tons of materials, every one of them started just like this, with a single chemist carefully mixing a few grams of stuff in a glass flask, just trying to get a new reaction to work. But taking that simple lab reaction and making it industrial, that's a whole different ballgame. Take ethanol, for example. Industrially, you can't just mix two things. First, you have to react ethylene gas with powerful sulfuric acid, all under really high pressure. Then, you take that product and react it with water. And finally, you have to separate and purify the ethanol you've made using these enormous distillation towers. It's a huge, complex engineering challenge.
And the end result is this just mind-boggling jump in scale. You go from a few grams at a flask to thousands of tons of material being produced for fuel, for solvents, for manufacturing all across the globe.
Now, this incredible power, the power to rearrange matter on a global scale, it has totally transformed our lives. But it also comes with a huge amount of responsibility. It really is a classic double-edged sword, offering us powerful solutions, but also creating some really profound challenges. Let's look at that ethanol we just talked about. On the one hand, you can blend it with gasoline to make gasohol, a fuel that helps us use fewer fossil fuels. That's a fantastic solution. But on the other hand, the wastewater from making it can contain organic stuff that bacteria and rivers love to eat. As they feast, they use up all the dissolved oxygen in the water, which can suffocate fish and other aquatic life. That's a serious unintended consequence.
And these challenges are everywhere. Our industrial world creates CO2 that's linked to a warming planet, it generates hazardous waste that we have to deal with, and it's using up some resources way too fast. Take phosphorus. It's absolutely essential for the fertilizers we need to grow food. But at the rate we're using it, we could face serious shortages in the not-so-distant future. But, and this is the most important takeaway, chemistry isn't just the source of these problems. It is also our single most powerful tool for solving them. Chemists are the ones developing smarter ways to treat waste, creating new methods to purify our water, and pioneering an entire field called green chemistry, which is all about redesigning chemical processes to be safe and sustainable right from the start.
At the end of the day, our understanding of molecules gives us the power to literally build the world around us. So the real question, the challenge for all of us, is to decide what kind of world that's going to be. With all this incredible knowledge, what will we choose to build next?